Hey there! In this lecture we're going to talk about NumPy, which is the short form of numerical Python. Since we know that NumPy is an efficient interface to store and manipulate data. So NumPy, it is a sort of interface which the data scientists use to store and manipulate data. And since we know that most of the job, about 70% of a data scientist's job is to manipulate and the data, is to play with the data, is to explore the data. So the first step that comes is that we need to store the data in a particular data structure. So NumPy is the interface that provides us the access to such data structures and which we can use them to store our data. So the important part is that we need to understand that the core of almost all data science tools in Python is NumPy. It is the basic founding structure for almost all tools, which include from TensorFlow to Keras to every other data structure which involves the manipulation of data, whether they be images, whether they be text. Mostly and widely NumPy is used for that particular purpose. We need to understand that NumPy, the sole purpose of NumPy is to use, create and manipulate arrays. So the data structure that NumPy provides us is with arrays in which we store the data, and the interface provides us with a lot of other functions which we can use to manipulate the data and play with it and explore it as well. So the data is mostly stored in arrays before it is fed to the machine learning algorithm. So in order to understand that we cannot just start processing the data directly and throw it into the machine learning algorithm, we need to store it in a particular format, and NumPy provides us with those tools, and it is a powerful resource which can help us to store the data in a particular format and to process it before we feed it into the machine learning algorithm. So in order to import NumPy as a package in Python, we use this particular syntax. Whenever we type this syntax in a particular cell in the collaboratory notebook, and in order to check the version of the NumPy, we use this np._version. So the question you should be asking yourself is, why are we using np? So it is an alias for the NumPy package. Whenever we are importing a package, whether it be NumPy, whether it be matplotlib or pandas, as we will see later on in the course, it is always better to use an alias, which is a short form for the same name of the package. And yes, it can be any other word as NumPy, but this is more of a convention, and about almost all of the data scientists use this alias in order to represent NumPy. So obviously it has some semantic relationship with the word NumPy as well, and so it's easy, and most of the data scientists, it is a sort of tradition and convention which is being followed and by almost anyone. So it is possible that you can use anything else, it depends on you, but it is rather not smart a way to use anything else, because if you go to online communities, if you want to read another source code, you will see that it is mostly represented in this way. So in order to follow conventions, in order to read other people's code, it is better to follow these traditions and conventions which are set by these data scientists. So let's talk about Python data types. We have seen when we were studying variables that there are different Python data types: integer, float, string. However, in Python there is no explicit data type declaration, which means that there is no explicit typecasting as well. As we saw earlier, we didn't have to declare the type of variable in which we were storing the data. Python automatically assumes, rather we should say that it automatically takes up depending on the type of data, and we do not have to explicitly instruct it that we are storing this particular data. For example, let's look at this C code. So in this C code, we have instructed that the variable x should be integer. If we try to initialize it with the string, the code fails. So this is an example of explicit data type declaration. In Python, we don't use that. We just declare it by 4, and we can also declare it by the string 4 as well. In this way, there is no error because we haven't fixed the data type to be integer in the first place. This is a flexibility that Python provides, and it's quite cool and makes things a lot easier. So let's talk about integers in a bit more detail. So as far as the code is concerned, we just need to initialize x, the equality sign, and we have stored the 1000 number in the variable x. But in reality, this is not just a simple integer or a container. It is actually a pointer to a C data structure that contains more information than just the value itself. So let's look at this code. So the variable x over here is basically pointing to the long object structure which contains information about the location of the object, the size of the object, and other information as well, which include the pointer and the value itself. So you can say that the Python variables and the different types of structures, data structures we use in Python, the backend implementation is still done in C. This is a rather complex situation when we study the backend implementation. So the reason we're studying is that we need to understand certain things. We need to understand why Python is an interpreted language and it's not that fast enough as compared to C++ and other languages like Java as well. So let's look at this diagram for a second. When we're saying that when we initialize integer in C, we call that the pointer, the variable itself is a pointer to the value, which is 1. But in Python, it is an object in itself which has the pointer as well as the value in itself. So this is a complete structure as compared to the C integer as well, which obviously requires more memory, which is not more efficient as compared to the C language. So in the two languages, we are getting a trade-off in terms of efficiency because C is obviously much faster and requires less memory as compared to Python, but Python gives us a lot of flexibility in terms of syntax and also is very easy to learn. So we have talked about Python lists earlier. We know that there are two types of Python lists. Firstly, we have the homogeneous lists. The homogeneous lists only contain one particular data type. So the all values in the list in a homogeneous list would be either int, float, string, or boolean. So the other type of list is the heterogeneous list, and this is the other flexibility Python provides us with, that we can store different types of values in the same list. We can store integer, float, string, and bool all together in one particular list. Considering the example of a homogeneous list, we can store, this is a list we call of integers. We have stored all integers and we can say that this is a homogeneous list. But at the same time, we can store boolean, integer, float, and string as well. So this particular list shows that in the same list, we have 4 different types of values. So this is another flexibility that Python provides us with. We can use the same list with the different data structures. And as I mentioned earlier, it comes with the cost of efficiency in terms of memory and computation as well. So let's look at a couple of syntax to create lists. There are different ways of creating lists. We can use loops to create lists, as the syntax in line 1 suggests, that we can create a list of range 10. So what this range 10 would do, it would select numbers ranging from starting from 0 to 9, and it would store in the list which would be named as L. The list syntax over here declares that the resulting values will be stored in a list which will be assigned to the value L. And if we want to check the type of the list, we have seen this syntax before. So if in order we want to find out the type of any data structure, we use the type function, and we find that the type of value at the index 0 is integer. And we can extend the same concept to other values as well. As you can see in this example, we have a list of strings which we contain words as well as alphabets. Although in Python, they're considered the same thing. But in the C language, characters are defined differently from strings. Let's look at another example of homogeneous lists in which we are going to typecast integers. If you can remember, typecasting is a particular concept in which we change the data type of different values. So if we have an integer, say 2, we will change the integer into a string. So this will be called the typecasting operation. So in order to apply typecasting to a list of integers, what we will say is that we're going to initialize an empty list, and we're going to use square brackets for that, and after that we're going to call a loop in which we're going to append the value of C in the list by using the append function. And as you can see, the string over here ensures that we are converting the integer C into string. And after that, we can print L2, and which would suggest that all the integers in L2 will be converted into strings. If you're thinking about whether this loop says that for C in L, we're talking about the L we saw earlier when we were talking about the list of integers. So this was the same list of integers which is called L, and we are indexing, we are iterating through over every value in L using C. So C is reading every value in L, and we're converting C using the string function. We're converting the integer value in C into the string by using the str function of Python, and we're appending into the list L2, and we're just going to keep doing that until the list is empty, and the L2 would be the same values, but this time they are strings instead of integers. So if you want to check out you have successfully typecasted the values, you can again use that built-in type function and find that out by checking the index value of one particular position in the string in the list. Let's discuss something. We have seen that Python almost gives us flexibility in providing us different types of lists. We can store different values in the same list. We can store string, floats, and boolean, and we can use the same list. So applying the concept of the Python integer, we have seen that although it is an integer, but in the backend we have used the C language to implement the entire structure, which is rather complex in terms and requires a lot of memory and computation when we're talking in terms of efficiency. So when we discuss the ability or the efficiency of Python lists, we discuss that there are different and many types of problems that arise with Python lists. So we need to understand that we have seen that even though we're talking about one particular integer, at the back end there is a rather complex object and that has a lot of information. So this tells us that you can say that if a particular integer has a complex object structure, if we have a list of several integers, we would understand that there are a list of several object types. So these complex object structures, now we have a list of them, and they're quite redundant, and they have redundant info. So we all know that the type of all the values in a homogeneous list is integer. So rather than if we have that information stored in a complex object structure, it's rather redundant because we already know that. So this covers up a lot of memory, which is not really required. So we have actually concluded that, considering the above examples, that although the Python lists are flexible, they are inefficient because they take up a lot of memory, and when it comes to computation, they are slower, and so we need an alternate for that. So we cannot just use Python lists to store data, because when we're talking about thousands or even millions of data rows and we need to store that data into a particular data structure, we need it to be efficient because we're going to perform a lot of operations on it. It is not efficient if it is not fast enough, if it requires a lot of memory, then it might become a rather tedious task for any data scientist, no matter how much he is skilled, and it will become harder and harder for him.